Okay, well, so today we have
Okay. Yeah.
the second part of German's talk about isolation theory. So we are continuing.
Mm-hmm. Thank you.
Fine.
So
Call is fine.
this time I will start with sharing my screen. Here we are. Oh, I have this file open. Good. So let me briefly
Yes,
remind
so this is previous talk. Wonderful.
what
You will recall
we
us.
discussed
Great,
last time.
great.
Now,
Um,
we decided to live in the three-dimensional space and talk about three lattices of rank 3, right? And well, we want to discuss this theorem by Castleton and Swinnerton Dyer, which is called an isolation theorem. And it says that given an algebraic lattice, if we slightly alter it so that the result is not proportional to the given lattice, then we will obtain a lattice whose norm minimum, even if it's positive, will be very small. And by the norm minimum of a lattice, we simply understand the following infimum over all the non-zero lattice points of such products, of the absolute values of such products, of the coordinates of lattice points. So to be more precise, given an arbitrary delta, positive delta, if we alter our lattice, by the way, given by this fixed matrix A, assuming that this lattice is algebraic, then there will exist some small epsilon such that for every lattice gamma in this epsilon neighborhood of lambda, for each such lattice gamma, the following statement will be true. There will exist a point B in this altered lattice such that the product of its coordinates will be, well, sandwiched between 0 and delta. And what is important, it will be positive. So, of course, we can obtain a lattice such that it has some non-zero points that belong to the coordinate planes, and then its norm minimum will obviously be equal to 0. But this is a kind of a degeneracy. We do not want to consider this as a success. So we want to find points which would satisfy such strict inequalities with delta arbitrarily small. And we observed that if our matrix, which alters the lattice, has such a form, then, well, in the, say, simplest case, when here we have just simple zeros, in some sense, it is the simplest case. We have a stronger statement. We have the following statement, which we formulated in the very end. For such an altering of our lattice, with this entry, say negative, well, we assumed it to be negative, but it was just for the simplicity of our picture, for the picture to be, well, uh, correct. But of course, it doesn't matter what signs this epsilon is. Now, the agreement is only that this epsilon is non-zero, and all the other epsilons are not greater in the absolute value than this one epsilon 1 2. So we showed that if our matrix B has such a form with zeros over here, then uh, then let us look at the picture. Then our three forms, our three forms of this kind, will satisfy the following three conditions. So the value of the first form, given by these entries, and its zero level is drawn here in red. So the value of the first form will be very small. We'll find a point V over here such that it will be close, much closer to the red plane than to the violet coordinate plane. This one. As for the second linear form, V happens to be far, happens to have a very large second coordinate, then, well, the deviation of this second, well, coordinate, okay, will not, well, change it much. So we can say that up to a bounded factor, it will be the same. But as for the third form, it will literally remain the same. So this is an important fact, and we see that we can find points W over here with the product arbitrarily small and positive. And as we see, well, this bound on the epsilons has nothing to do with delta. So actually, this epsilon can be arbitrary, just fixed, and that's it. So having fixed, say, this quadruple of epsilons with non-zero, with not all of them zero, we know that, well, we can find a point V, maybe very far, which will have a very small product of the new coordinates. Okay, and particularly, as Nikolai commented last time, this first case, this first one, in this context, we can use the term unipotent flow, right? So for such a trajectory, we well know that something is everywhere dense. But what is everywhere dense? Here in this context, we know that the set of the values of the product of such three linear forms will be everywhere dense if we look at the values at our lattice points. But the statement here reads as follows. There's just an epsilon which depends on delta, such that every lattice and so on. So now the question is, what happens if we allow our matrix B to have arbitrary elements, arbitrary epsilons, with the only restriction that they are all bounded by some fixed small epsilon, which depends on delta, which may depend on delta, and with the agreement that this one is the greatest among all the epsilons, and it is non-zero. Well, let us discuss this this fourth case, case 4. So case 4. Case 4, well, let us copy what B looks like. Where is it? No, here it is. We have B with arbitrary okay, let's copy everything. Okay, so now our B is an arbitrary matrix of this form, right? And we assume that epsilon 1, 2 has the greatest absolute value. Now, let us once again draw a picture. And I will probably copy this one and show what happens if the third form is non-trivial. So the 0, okay, let it be the 0. Okay, let's preserve everything here. Okay, and so we'll take this picture. Yeah, okay. Now, what do I want to draw? I want to change slightly the picture. I want to make it a bit more delicate. So probably I will delete, yes, probably everything in here. Okay, and now why do I want to delete it and draw something more delicate? Okay, look, I want to have something very small here. Okay, well, here we'll have respective copies of these hyperbola, right? So now, if I repeat the picture, so I want to consider the 0 level of this simpler form, right? So say somewhere here, no, blue, somewhere here, I will have the 0 level, this form, like this, right? And well, I have something close, right? So repeat. We have this yellow line, and so here we have this yellow segment. Here I have such a this is that very same parallelogram. I call it a parallelogram because its image under the logarithmic map is a parallelogram. And we find a point inside this parallelogram, say point V, right? And if I look at the actual first linear form, then it will give me such a red plane. And still the point V will be pretty close to the red plane also, okay? Now, if I allow, okay, the form L2 is simply 2, 1x plus y plus 2, 3z. We we can, well, forget actually about this form because once again, if the second coordinate of this point V is huge, then this value is pretty much the same up to some bounded factor, okay? But the third form is important. 3 epsilon 3 1x plus epsilon 3 2y plus z. Now, we only know that all the epsilons are bounded by the epsilon, and epsilon 1 2 it is the greatest among them, right? So what can happen? So we make this form. So this one becomes small. This form remains almost the same. Remains almost the same. Okay, but this one can actually grow, can become huge. Can become huge. And this will ruin everything. So we have assume that we have made this form small, right? This is approximately the same, but this form became huge and it neutralized the property of this form to be small, right? So now, why did I need a more delicate picture here? So I want now this distance from V to the horizontal coordinate plane to look small, okay? Now, this distance, this red distance, is determined by epsilon 1, 2, right? And as for the epsilons 3, 1, and 3, 2, we only know that they are bounded by this epsilon 1, 2. So actually, we could have, say, if we, well, for instance, if we prolong it somewhere here, and we'll consider what this third plane, right, the zero subspace of this linear form looks like, then, for instance, it can look as follows. So this would be, say, something like this. So probably it's reasonable too. So this is the zero level of L1, right? So it can happen that, well, it can happen so that, well, say, we'll have something like this. The zero level of L3. And then what? Then, indeed, well, if we look at this distance at the third coordinate of the point V, well, if the second coordinate is huge, and well, the first one is, well, is it is equal to the second coordinate times some uh, fixed factor determined by, you see, this thin cone, right? By this direction, actually, right? Then we conclude that the third coordinate of this point V will be very small. And if we compare this third coordinate with the distance to this deviated plane, then the ratio will become, well, something similar to what we have here in this, where was it? In this picture, right? So we made the first form very small uh, with the help of finding a point there where this ratio is very small, right? But again, it can be well, this smallness, this property of being small, can be neutralized by this huge value of the third linear form, and, and that is very bad for our purpose. We are not able to prove anything with this assumption, but nevertheless, what do we know? Uh, our basic, well, the core of our argument is the following Kronecker type theorem. So if we place such a parallelogram of this shape wherever we want, we will find a lattice point. A lattice that lives here in the logarithmic plane, and it consists of the images of the points that are representatives of the units, right, of our extension. Now, so I can place this parallelogram of this given shape anywhere I want. So what do I want to do? Well, even if we'll still look at this first picture, we can actually, well, if this plane, this first one, is very close to the YZ coordinate plane, then with the fixed value of Y capital, we will obtain, well, this green parallelogram somewhere up here. So if we fix our Y capital, then, well, this shape becomes fixed if we fix Y, because this is the surface H, X, Y, Z equal to 1. So now I want my deviated form, outer form, to be close enough to the first linear form. to the form of the first coordinate, so that this parallelogram is high enough. And if it is high enough, then I will have the following picture. So this picture looks, well, very bad, because L3 can become huge and it will ruin our product. So I want to draw a picture of probably this kind. Which kind? Which would be okay. Let me take this one. So, boom, 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 boom. I think this will be almost the last picture. So what do I want to delete? I want to delete all these things. Okay. I will not be able to delete it without deleting. Yeah, it's complicated. Okay, I managed to do it. Okay. I let's do this. Okay, I will repair this. Okay, now, what do I want from my picture now? Well, I want my first form to, well, look like this. This will be thin sector. Okay, this thin sector, and here we have our yellow line. Here we have our yellow segment, and next the green ones. This, oh, oh, something like maybe something like this. Okay. And what did we color it? Yes, here we colored it. Follows. Same thing can be done here. And I find a point here, B. Okay. Now, the effect that I want to use is that this point is, well, high enough so that its third coordinate is not too small, right? So given some bound y capital, say, as I did draw it previously, I try to color it violet. Okay. Now this is the plane, say, now this is the plane y is equal to y capital. And I want it to depend on delta. Now, having this y capital fixed, and well, how does it depend on delta? Well, the way, so I think we called it lambda here. We have this statement for every omega here, arbitrarily small, there will exist a lambda which will determine y capital, right? Such that this parallelogram contains a lattice point. Now here, in our picture, we have this parallelogram, this pre-image of our parallelogram, having this thin width, which would denoted by omega, considering its image under the logarithmic map. And well, this lambda, say we had this lambda in the logarithmic space, its length, right? It depended on omega, so if omega is determined by delta, then of course y over here, y capital, will be determined by delta. So having these parameters fixed, now I want to make epsilon small enough so that this parallelogram is high enough. And then, well, if I consider my altered first form, well, it will be somewhere here, maybe, I don't know, maybe I can draw it like this. So this would be my altered form, the first one, right? Okay. This. So now this is the zero level. I can copy it. The zero level of L1. And well, look, wherever the zero level of L3 is, well, it is somewhere, say, in this picture, it will be, well, the intersection with this, say, plane y equal to y capital will have such a rather thin stripe that will contain the intersection with the zero level of L3. So the zero level of L3 will be somewhere, well, say, I don't know, here or here, maybe. It doesn't matter. There's the zero level of L3. And now we see that, well, if our epsilon is small enough, and this parallelogram, quasi-parallelogram, is high enough, then the value of this, well, third deviated, altered linear form will be approximately, well, the same as the third coordinate of V. At least the ratio will be bounded. So having having made epsilon small enough, we obtain this good situation that this point came somewhere up here, right? So that the value of L3 cannot, well, grow too much. So in this situation, so having chosen epsilon, depending on delta, small enough, we guarantee that, well, how did we write down over here? Guarantee that L3 of V is of the same order as V3, whereas L1 remains small and L2 remains approximately the same as V2. So this is it. This is the proof, actually. Then, well, the product L1 of V, L2 of V, L3 of V is can be bounded by delta being still positive. Now, concerning this last condition that it is positive, you see here in this picture, it is actually quite obvious. Now, why is it obvious? Well, because you see, I can actually, it is reasonable to copy this thing, this zero level. Okay, this one, copy. So I want this to, I should pull it down a bit. This. So this is the zero as previously. This is the zero level of L1 prime, this simplified form, right? And look, oh, there's a mistake here. I should not. This red line actually coincides with the blue one. How can I amend it? Guess I will have to. Okay. Have to repair it like this. Okay. And here we have this next. Like this, right? Here goes the blue line. Yeah, now it seems more appropriate. So how did we obtain this red altered plane? So the vertical blue one, this, well, we called it somehow sheets or pages, right? We call them pages like this. So these blue pages, they all pass through the vertical coordinate line, okay? And well, because they have such form, okay? And if we put something non-zero over here, the intersection with this plane will be this very blue line lying in the horizontal coordinate plane. So the red plane will be obtained by rotating the blue page around this line in this direction. So if I choose my parallelogram to be, say, on the left hand side from the vertical blue page, right? Then, well, this new red not contain this point V that we catch inside this parallelogram. And this provides that the value of the first linear form is small but distinct from zero, whereas the values of the second and the third forms are something not small. Okay, so I hope I managed to make it clear. I mean, the argument. So this is how we, well, repair the possibility that third form can become huge. We repair it by making epsilon depend on delta. Okay, and this is the picture. Was it clear, or do I need to explain something else? No questions? Okay. I hope everything is clear.
Well, what's the problem?
I'm asking whether everything is clear or not.
Yeah, I think as for me something is clear, and later I would like to ask one question, but later.
Okay. Well, actually, I have completed the proof of the isolation theorem. And, well, I can now show how to derive, say, Littlewood's conjecture from this Castles-Swinnerton-Dyer-Margulis conjecture, if you would like me to do it. What will be your choice? Are we going to derive?
Both. We will not. We do not have time for both of choices.
For what?
Do we have time for both of choices?
For both what?
For both. Both. Оба choices.
Both what?
Вы спросили,
Какие choices?
you ask, что мы хотим, you ask what we prefer. А мы prefer оба и то, и то. Нет? Ой. What's...
I have completed the proof of the isolation theorem. And now I can derive Littlewood's conjecture from Swinnerton-Dyer Castles-Margulis conjecture. Do we want it or not? or is the isolation theorem enough for today?
А,
Actually,
я как раз и говорю, it will be better, it will not take too much time to...
no, it will be, I can do it pretty fast.
I think
So I'm doing it. Oh, okay.
it is
Okay.
reasonable.
Now,
Yes.
кто-то времени даром не терял. So, let me copy these two conjectures and place them over here. Make them small. Do the following. Like this. Like this. Now, what I want to do now is to prove that if this statement is true, then so is this one. This. Okay, assume that there is a counterexample to Littlewood's conjecture. Assume that alpha, that there exist alpha and beta in R that provide a counterexample to Littlewood's conjecture. Oh, well then, that is, how can we write it down? So, say x times, x times alpha x minus y times beta x minus z, right? Is bounded away from 0 by some delta for all x, y, z integers and x positive. Well then, okay, let us consider a lattice, the following lattice. A lattice, how do I want to call it? Okay, let it be lambda. Lambda, let it be defined as follows. So we take, say, 1, 0, 0 here, right? Then alpha minus 1, 0, and beta 0 minus 1 times z. Okay. Then lambda is admissible for the following set. Okay, say the set of points, say x, y, z in R3, such that first of all, x, y, z is bounded by delta, right? And maximum of, say, y and z, the absolute values, is bounded by 1, by the unity. So by admissibility, I mean that, in the interior of this, it's open, right? So there are no lattice points inside this set, right? So there can be points on the boundary, but there are no non-zero. I forgot to mention non-zero lattice points inside this set. Well, how can we call it? How can we call it? Call this set? I don't know, M. Now, if we consider the following diagonal matrices, say D, say T, matrices of the following form. So we contract the first coordinate by, say, I don't know, e to the minus 2t, and expand the second and the third coordinates, e to the t times. And say, I don't know, t, let us extend it to plus infinity. Then obviously dt lambda is admissible for dtm, clearly, right? And well, the limit set as t tends to infinity of dtm is clearly simply the set of points x, y, z in R3. Such that simply x, y, z is bounded by delta. That's it. But by Mahler's compactness criterion, among all these, well, if we consider this set of lattices, this trajectory of lambda, then it will have a limit point. Well, see there, well, it exists a sequence of t, c, I don't know, t, n, such that, well, tn tends to infinity as n tends to infinity, and d tn lambda tends to some lambda prime. Then lambda prime is admissible let us call it M prime. Right? That is the norm minimum of lambda prime is positive. So by Castle's Swinnerton-Dyer Margulis conjecture, we conclude that this lattice should be algebraic, or well, similar to an algebraic modulo the action of the group of diagonal operators, non-degenerate diagonal operators. So by Castle's Swinnerton-Dyer Margulis conjecture, lambda primus is similar to an algebraic lattice. And we can apply the isolation theorem. So however, in each epsilon neighborhood of our lambda prime, there will be well, a point of this kind. Here are lattices d tn lambda, right? And for each of them, the interval, say 0 delta, the interval 0 delta. Now, what is delta? Delta is this thing that bounds the product. And if we forget about the points of this lattice that have the first coordinate equal to 0, then all the rest of them, all the other lattice points will have the products of coordinates bounded away from 0 by delta. So this interval is free from values say product v1, v2, v3, where v belongs to our to d tn lambda. Now this contradicts the isolation theorem. That's it.
Wow.
This is the argument, and I actually didn't even have to draw the final picture that I actually had in mind, but everything probably is clear even without a picture, is it? What can you say? Can you say anything? Yeah.
I do not understand well what are you asking. You just finished deducing Littlewood. Yes?
Yeah.
Yes?
I have proved Littlewood. Yeah.
Proved Littlewood, yes.
Yeah. But with the help of this very strong conjecture. Any questions?
Any questions, comments?
Okay. So I guess those who will be interested will have a chance. Well, those who did not reach us today will have a chance to
Yes, we will put it on the web very
look
soon, and I will send the links to everybody who was involved to our previous.
online.
Wonderful.
Okay.
Thank you very much. Now we will stop recording.
Okay. Thank you.